What up, dudes? All right, we're talking about logarithms. We talked about inverse functions. And then really quickly, before I get really deep into it, I want to show you this. In order to, all right, so let's go back to that y equals x squared. Cool? And I already know that the inverse to this is y is equal to plus or minus the square root of x. Right? I know how to find, I know that that's the inverse. And then let me ask you this. How did I find that? Well, I found that originally by just graphing it for you and saying, look at this, and then the inverse is actually this. Doesn't that make sense to you? And you said, no, yeah, okay, fine, that kind of makes sense to me. But the official way to find the inverse is actually, what all you do is you just say, look, to do something inverse, we just take the input over here and the output over here, and we switch them, right? So if I want to find the inverse in the official way, I would just say, all right, fine, then I'm going to switch and go x is equal to y squared. Are we cool with that? Now, I can't say that these two are equal, but this is after it undergone the switch. I just switched x into y. Whoop. And then I solve for y because solving for x always seems funny for me, so I solve for y. If I want to find y, I want to take the square root of both sides. If I take the square root of both sides, I have to add in the plus or minus. So I have the plus or minus the square root of x is equal to y, and hence, that is how I got my inverted function. Are we cool with that? All right. Now, with exponential functions, things get a little weird. Because exponential functions look something like this. Some number a to the x power is equal to y. X is your input, y is your output. And we know this, right? Now, here's the hard part, is let's do the switch. So then this becomes a to the y is equal to x. That wasn't hard. I just switched to x and y's. Here's the hard part. How do I get y all by itself? There's no real good way to get y all by itself. I can't have y is equal to something. I don't know how to solve for y in this case because it's an exponent. I mean, if a were in the exponent, I would know exactly what to do. I would take the 8th root. But in this case, I don't know how to solve for y. So what we need to do is we come up with a new notation, and I need to show you this. So write this down. Take notes on this. Notation. Notation is the word that you use for when you want to explain what words you're using. And if I have something like y is equal to a to the x power, let's see. No, I'm sorry. If I have something like a to the bth power is equal to c, okay, that translates to log base a of c is equal to b. All right? Now, this little number right here is called the base, and I'm all about it. That base. About that base. No treble. I'm about that base. All right, anyway. That's what the little number is called. It's called the base of the thing. And the C is actually what your answer is, and then the B is what I guess your answer is. Here, let me show you something like this. Watch. If I go like this, 2 to the x power is equal to 8. Can you tell me what the answer is? It's 3. Bradley, how did you figure that out? Yeah, no, you guys all got it. Right, okay, so 2 to the 3rd power, because you thought in your head, well, shoot, that's not hard at all. All you got to do is like 2 times 2 times 2 is equal to 8, right? So if I do it 3 times, it will equal to 8. The answer is 8. X equals 8. Well, in log version, you can write this as log base 2 of 8 is equal to, and if you plug that into a computer, then you will get the answer. The answer is 3. Log base 2 of 8 is equal to 3. Something that I do to try to help me to remember how to translate this is I always write this down. Log base A of C is equal to B. And I always have trouble remembering how exactly it looks like in this form. I kind of think of it as like a scorpion. You know, a scorpion has a tail that kind of comes around like this. So I kind of think of it like this. The scorpion goes around like this, through here. So, A to the B is equal to C. Because you got the A, you're going to hit the B, you're going to cross the equal sign, and then you get the C. I don't know if that helps. We cool? Now, what is the point of all of this? The point of all of this, well, you can answer the question for simple. You can get an answer for simple questions. But what's really cool about logs, Bradley, is what if I asked you this? What if 2 to the x is equal to 10? You would say, I don't know. Because 2 to the 3rd power is equal to 8. But I can't tell you what 2 to the whatever power is equal to 10. I don't know. It's very hard for me to do. You know what I mean? Yes, exactly, Lucas. What you would do is you would plug into a calculator log base 2 of 10 is equal to what? There we go. Are we cool? And then you plug that into your calculator. If you go to Wolfram Alpha, I would plug in the letters log underscore 2 parentheses 10. And I think Wolfram Alpha will figure out exactly what you want. And it will give you a number. And I'm guessing that the number is probably going to be like 3.37654. I don't know. Yeah, the log button now has a purpose on your calculator. No, this is log with a subscript. It's an underscore. Yeah. It's not a log minus 2. It's log base 2 of 10. All right, but here's the thing. Whenever we write down log, we almost always assume that A is equal to 10. So if I were to just tell you what is the log of 4, what I mean is, what is the log base 10 of 4? Does that make sense? Or maybe we'll do it like this. What is the log base 10 of 100 or 1,000? Let's go with 1,000. Okay? So what's the answer to that? All right, so here's how you do it. Remember? You set that equal to x, and then you say, all right, wait, let's do the scorpion. 10 to the x power is equal to 1,000. How many times do you have to multiply 10 by itself to give you 1,000? 100 times? Nope, not even close. Three times. Very good. Does that make sense? Because 10 times 10 times 10 is 1,000. We cool? Yeah, there's 3 zeros in 1,000, so 10, blah, blah, blah. Are we cool with that? Now, what is the point of all of this? Like, why the heck are we learning about all of this? So real quickly, just to recap, this is the general equation for a log right here. So write this down, and then write down its counterpart. These mean the exact same thing. This is just another way to write it. This is another way to write it and solve for the exponent and get it all by itself. The exponent is b over here. That's what I wrote over there. This is the notation. Now, if a is equal to 10, that is the most standard log that we deal with. That's called log base 10. And if you type in the log button into your calculator, it assumes that you're talking about log base 10. Cool? Now, there is a special magical number in this universe, and it's called E. And it's like 2 point, I forgot what it was. But I already introduced it to you. It's that same y is equal to e to the x power. It's the exponential number. We cool? You've seen this before. So if I let it log base e, that is what we call the natural log. Because base 10 is a really good base for us to use because humans like to use it because we have 10 fingers. Literally, that's why. Like I'm telling you, that's the actual reason why. But then we said, wait a second, there's this really magical number called E that lends itself really nicely to this thing. And when you take calculus and all this kind of stuff, you're going to realize this is amazing. Anyway, scientists love to use this. This is the main go-to for scientists. Whenever scientists deal with logs, they have log base E, which we call ln. You probably see ln somewhere on your calculator too. So there's two versions of logs. Well, there's actually three. There's the most general one, which is probably the least useful. There's the log base 10, and then there's the natural logs. Are we cool? All right. Why the heck do we even care about logs? Well, see, logs, I guess it kind of goes back to one of those times when we didn't have a calculator and we needed to know how to multiply like gigantified numbers together. And we didn't know how to get that answer. Does that make sense? So then what we did was we said, all right, well, what we're going to do is we're going to invent this thing called logs, and we're going to make a table of the most common ones, the easy ones to figure out. And then using that table, we can now calculate all kinds of things with a pencil and paper. When I was on a test, I actually had to do a problem that said, like, what is 2 to the 47th power? I'm curious to know, if you type in 2 to the 47th power on your calculator, what is it going to tell you? That's 2 caret 47. Does it give you an answer? I know it's not. Well, no, it should be a whole number. There's no way it should be a decimal. Oh, I see. The computer ran out of space in order to figure out the answer. Is that what happened? Oh, I see. It's e to the 14th power. Okay. Well, using logs without a computer, I can figure out what this answer is. I could have told you that that was the answer. That's how powerful it is. In fact, actually, this might be embarrassing, but let me see if I can figure it out right now. What I would do is I would take the log of both sides. Is equal to log of x. And then there's this property that says if you have log of something to the to the 47th power or something where there's the exponent over here, you can take that exponent and just multiply him right out in front. So this becomes 47 times the log of 2. It's the property of logs, and that's what makes it amazing. What is the log of 2? Just type in log 2 on your calculator. Tell me what that is. So what I would do at this point, if I were some mathematician back before calculators, is I would look up in a table what the log of 2 is. And that's easy to do. But I don't have that table on me. So what is the log of 2? It's 0.301. So then do me a favor. What is 47 times 0.301? $14.147. Okay. So look, watch how I do it. Okay. This thing comes, the scorpion's a little bit backwards, but it comes around like this. So then you go 10 to the 14.147 is equal to x. And then you say 10 to the 14th is, or times 10 to the 0.147 is equal to x. And then I can say, well, 10 to the 0.147 is just 1.407. So this answer is 1.407 times 10 to the 14th power is equal to x. So without using a calculator, well, with using just multiplication and all of that kind of stuff, I got you this answer, which your calculator had to do. It's either that or I sat down and did, okay, what's 2 times 2? 4. Times 2, 8. Times 2, 16. Times 2, 32. Times 2, 64. And I did that 47 times. This is the answer you would get. Are we cool with that? Now, I fully don't expect you to like really completely understand every single step that I did here. I just want to show you the power of this, how cool it actually is. But anyway, that's the power of logs and what it does and why we have them. A lot of what our computers do is all based on logs. So if you want to know how to program computers, not necessarily like how to program computers, but how to like be the next person who invents the next programming language to program computers, then you would learn about logs and all of that kind of stuff. It makes our lives really easy, much easier. And it's really great for doing things like you could do 2 to the 47th power, but what about 2 to the 470th power? Now, maybe your calculators can do it, but I'll tell you why they can do it. I know exactly why they can do it, because they know how to do logs. But I'm telling you, if you type 2 to the 470th power into a different program, it wouldn't know what the heck you're trying to do. It would say that number is too big that I'm just going to break. And yet, you know how to do it. And yet, I can do this on paper and pencil. Anyway. Let's look at number 29, because I have a feeling I answered number 5 for you already. Actually, I'll tell you what, let's look at number 5 real quick, just real quick. Okay, all right, so 2 log x plus 4 plus 5. All right, this isn't really a problem about logs. It's about transformation. And we know that the log function, the parent function, is going to look like that. And what I mean by parent is that's the standard good old log, just y is equal to log of x. We cool? And then when you do this plus 5 thing, it pushes that log thing up by 5. This plus 4 thing moves the log to the left by 4. And then this guy stretches him vertically by 2. So I'm betting the graph looks something like this. Yeah. Number 5 wasn't actually something to do with logs. It just had a log in it, and then you guys freaked out. But I told you that you guys could solve that problem before you even... Oh, how would I simplify it? Did I ask you to simplify it? No, it didn't ask you to simplify it. But I told you how to solve that problem without even doing or knowing about logs, because you know what an exponential function looks like. And then you know that, well, that's just not an exponential function. All right, let's see. 500 times 3 to the t power times 3 to the t power is f of t. Okay, so this is an exponential function. We know that the growth is 3. It's growing by a factor of 3 every year, and it initially started off with 500. But the question is asking, if the output is 50,000, what was the input? Okay, well, here's what you would do. You would go, all right, let's see. So here's what I would do. So I have 5,000 or 50,000 equals 500 times 3 to the t power. We go with that? So would it be all right with you if I just wrote this? I'm going to divide both sides by 5, and that makes it a 1 and a 1. I'm going to knock off 2 zeros. So I have 100 is equal to 3 to the t power. We cool? All right. Let's write down that one equation. Log base A of log base A of B is equal to C. No, I'm sorry, it was this. It was backwards. C is equal to B. And then the equation goes like this. So it's A to the B power is equal to C. So if I have this, I can make this thing by making it, here's my A, which is so log base 3 of my B was, so that's equals to T, and then this is 100. Are we cool with that? You see how I got from here to here? I use this formula to translate it. All right, now go to Wolfram Alpha and then just type in log sub 3 of 100. And what do you get? Actually, you know what? You don't need to even plug it in. The answer that they gave you was, they said, what? They didn't ask you for a number. They just said, which one of these solves it? So the option is this. That's what the one you would choose. Now, there's more advanced stuff. Like, how do I change this 3 to a 10? Because I told you before that the logs usually base 10, not any other number. There's more advanced stuff that you would do. Or, how did I know that I take that thing that was in the exponent and I can just drop him down in front? Like, that was a pretty cool thing, right? And those are advanced things. And I don't think that I have time to teach you before Friday, Bradley. I think you're just going to take your test and do the best you possibly can with that. I can't teach you the advanced stuff, but apparently, at least in the example the example problems, they didn't ask you to do anything crazy with it. All they asked you to do was use this formula to translate it back. And really, this is a correct answer, but this answer is when you're solving for t. Anyway, I'm super late for physics. I think that I was supposed to start at 11:20 or 11:10 or 1:10 or something like that. But I'll just call them up and say, I'm sorry. Anyway, did that help? Did that make sense? Am I going to assign homework for logarithms? I'm going to say no. In fact, I just finished your final exam, and I'm going to probably try to give you your final exam. I was telling the students today. Let's do this on recording. I was telling the students today that I feel kind of bad because, at least for the 11th graders, for you 10th graders it's not so bad, but for you 11th graders, you had to take the ACT math test this year. You had to take the EOC math test, and you had to take the SBAC 2 math tests. Pretty much all in the 4th and 3rd quarter, right? So what I'm going to do is I think that I'm going to basically just back off on the final exam. It's not to say that I'm not going to give you one, because I'm required to give you one. But it's going to be easy. And you'll have lots of time on it. I can't say easy because when I usually say easy, you guys always tell me, no, it's hard, whatever. No, I think that I'm basically going to give you like an all-day thing. So like if it's timed, it's going to be like 24 hours. Or a week. 12-hour time. Yeah, all right, something like that. I'm not going to make it so that it's like high pressure. You got to do it, crazy amounts or whatever. Anyway, that's my idea. I could go back on my promise, but that's essentially what I'm thinking. And the reason why I'm thinking that is because I'm backing off on how many questions it has. Cool? All right. I'll talk to you later. Okay, bye.